So now that we've introduced a totally new quantity, reactance, we're going to introduce another totally new quantity called impedance. And impedance is the most powerful concept in AC circuit analysis, and soon you will see why it is so super useful. So our impedance, I'll just jump right in. Our impedance is a new variable, capital Z. I usually cross my Z's, and it takes different values depending on we're talking about the impedance of a resistor or a capacitor or a inductor. And what we have to adjust to here is this is not necessarily a real number. This is now a complex number that we can express as a real and an imaginary part. Or we can express it in polar coordinates as like a magnitude and an angle. So we'll talk more about the complex number part in a little bit. So the way this works is the impedance of a resistor is just the real value R equal to the resistance. And the impedance value of an inductor is equal to J times, or sorry, I should preface this. So the imaginary part, for our imaginary number, rather than using I, because I is taken by our time-dependent current, we are going to use J as our complex number, the square root of -1. Okay, so our inductor impedance is totally imaginary. It's totally on the imaginary axis, and it is equal to J omega L, and I should say this is equal to Jx. So really our impedance is related to our reactance. The reactance is just like the magnitude of the impedance for the inductor, and as we'll see, the capacitor. So our capacitor impedance is equal to 1 over J omega C, which is equal to minus J times 1 over omega C. So 1 over J is equal to minus J. So either of these are the same, and this is equal to minus J times our reactance. Okay, so why is this useful? Well, what's going on here is this complex number is taking into account the phase shift between the current and the voltage. So this impedance is still the ratio of our voltage to our current. This is still V over I, but now we can also have V and I be complex numbers, and the angle of that number can keep track of this relative phase shift. The magnitude is just the magnitude. Okay, so we'll get to some examples of this, but a couple more facts to talk about. So this relationship is true for each component, or we could also write this as I is equal to V over Z if we want to think about, if we're applying a V divided by the impedance to get the current that results from that. So this is true for each component, meaning each electrical component. If we're going to write these in polar form, since we're already doing this, J omega L, so now it's going to be useful to look at things on the complex plane. We will be doing a fair amount of this. So this is like the real axis. This is the imaginary axis. So J omega L, omega and L are real numbers. So if we multiply that by an imaginary number, we get a purely imaginary number, which means J omega L is somewhere up here. It is on the positive imaginary axis. And that means this angle, this phase angle that we get, is plus 90 degrees. So we could rewrite this jx as omega L with an angle of 90 degrees. So this is a way we can represent the magnitude and the angle of our complex number. So this is like rectangular coordinates, this is like polar coordinates. We can do the same thing for the capacitance. Now minus J is going to be down here. So if we have a complex number like that, its angle is going to be minus 90 degrees. So this is equal to 1 over omega C at an angle of minus 90 degrees. Why is that useful? Okay, so if V and Z are also these complex valued thing where the phase is telling us, where the phase of the complex number is telling us the phase of our oscillation, when we divide V by Z, dividing complex numbers with phases, actually the way the math works out is very easy. Like the phase of I here is the phase of V minus the phase of Z. So you divide the magnitudes, you divide the magnitudes of V and Z and then subtract the angle of Z from the angle of V to give you the angle of I. So that's why polar coordinates are useful for this. All right. So while I'm erasing this, where is all of this coming from? So I'm skipping over some of the underlying math, but the short idea is this. If our oscillations, we can think of oscillations as being something that's following this sine wave trajectory, but a sine wave is just one projection of something moving around in a circle, right? It's like if we look at a circle moving on a plane, like the x-axis, if we look at the motion of this dot as it moves around the circle at constant angular velocity, the x position is tracing out a sine wave on here, right? So if we imagine a complex number going around here, so this is like a complex vector on the complex plane going around, well, its real component is like that same oscillating thing. And it turns out the way these vectors combine preserves all of the phase aspects that you get from the like derivatives and integrals you do of the sines and cosines. So you will see it's a lot easier to deal with these complex valued things than to try to combine sines and cosines that are different phases. Okay, so how the heck do we use this? So we're going to just jump in with an example. So let's say we have a circuit like this with a AC voltage source and a resistor and a capacitor. Okay, so the resistor is 1 kilo ohm, the capacitor is 1 microfarad, and the voltage source here is 10 volts. Oh, sorry, it has an amplitude of 5 volts. And its frequency of oscillation is 100 hertz. So this is not omega, this is our normal F frequency. Okay, so here's where impedance gets super cool. So we have these two things in series, and it's like, oh, I can't combine a resistor and a capacitor the way I might be able to combine two resistors, because these are totally different things. But impedance. So here we have an impedance for the resistor, ZR. Here we have an impedance for the capacitor. And this circuit is effectively the following circuit, where we have a voltage source and one general impedance, where this is equal to ZR plus ZC. So when we have two impedances in series, we can just add together those impedances to get the total impedance. This is super useful because we know how to do that. Okay, so let's look at some actual numbers here. So ZR is just 1K. That's really easy. ZC we don't know, but we can figure it out, right? So it's 1 over J omega C. So that is equal to 1 over, I guess I should, I'll just put this at an angle of minus 90 degrees. So that does the 1 over J part. So Omega is 2 pi times 100, and our capacitance is 10 to the minus 6th. And when we plug all those numbers in, we get 1,592 ohms with an angle of minus 90 degrees. I may have neglected to mention before, the units of reactance are also ohms, even though they're not a resistance. This is why we can add them together. Okay, so we have these two impedances. They are at different angles, but now we can think of combining these. Well, if we're not comfortable with complex numbers, we can think about combining these like vectors. So on our complex plane, we have something that looks like this. We have on the real axis 1 kilo ohm, and then in the negative 90 degree direction, we have 1,592 ohms. And so our total impedance, maybe I should call, well, I erased it. The total impedance, which is going to be, the vector from here to here, I will draw that in a different color. Call this Z total. That is just equal to, we can represent it in rectangular coordinates, just like 1 kilo ohm plus 1592 times minus J, or minus 1,592 times J is probably a better way to do that. Or we can represent it in polar coordinates. So there, we just need to find the magnitude of that. So that's the square root of 1,000 squared plus 1592 squared. And that is 1.88 or 1,880 ohms. And the angle here of this, you can see we expect a number, it's still going to be negative, but it should be less than 90 degrees. Maybe if I drew this to scale, maybe 60 degrees-ish. So theta here, the angle, below the x-axis, theta is going to be the inverse tangent of, so opposite over adjacent, so that's 1592 divided by 1,000, or 1.592 over 1. And this gives us an angle of 58 degrees, but of course, that's telling us the magnitude of this angle of the triangle. We know that it is in the negative direction, so we got to put a minus sign on that when we actually include it in our Z answer. So Z total is equal to 1,000 minus 1592J, or we can rewrite that as 1.88 kilo ohms into the minus 58 degrees direction. Okay, there is a huge amount of information contained within this, because this is including the effects of the resistor and the capacitor simultaneously. So, how do we use this to figure out what is going on? Well, remember that our current is equal to V over Z, right? So that means that our 5-volt oscillation divided by 1.88 kilo ohms at an angle of minus 58 degrees. Remember, this is implicitly at an angle of 0 degrees, because that's, if we're not told the phase of this source, we're assuming that it's, we will use this as the reference and call this 0 degrees. So dividing this out, 5 divided by 1.88 is going to give us 2.66, and that's volts over kilo ohms. That's going to be milliamps. And 0 degrees divided by minus 58 degrees, meaning that we subtract this from that. 0 minus 58 is going to be plus 58. Okay, so this is our final answer for this. Now let's interpret what's going on here. So we found a magnitude of current that we get oscillating in this. So our magnitude of current is 2.66 milliamps. The plus 5.8 here is the angle of the current relative to this 0 degree angle of the voltage. So if we're looking at the voltage and the current on our real and imaginary axes, if our voltage is a vector like that, and we can imagine this being this vector that's rotating around at this rate omega, right? If this is rotating around at this rate omega, so I guess its angle is equal to omega t, right? It's going around like that. Our current is at an angle of plus 58 degrees, so it's like this. So this is V, this is I, and it is also rotating at omega t. So there's this relationship between the voltage and the current, and you can imagine those rotating around, or you can imagine their x components, oscillating back and forth. We'll look at some graphs of this later on, and you can see how it fits together. But the cool thing is, from this, we're combining the resistor and the capacitor into one value, the impedance, and using that, the magnitude of the impedance to get the magnitude of the current, and the phase, the complex phase of the impedance, to tell us the phase relationship between the current and the voltage. There's one more thing we can do with this that I want to show you, and that is looking at what's going on with the resistor and the capacitor individually. So for this, there are a couple numbers that we're still going to need that I want to leave up here. So we're going to need the capacitor impedance. So that's this. The total impedance we'll hang on to. We'll get rid of that diagram. And I'll keep this current, but I'm going to write it over here. Plus 58 degrees. Okay. Yes. I'll erase that. Okay. So for the resistor, now let's just look at what's going on for the resistor. So for the resistor, at any particular, we have this voltage that we're applying to this circuit, but we don't know how much of it's on the resistor and how much of it's on the capacitor yet. But we do know this current, because these two are in series, this current is flowing through both of them, right? I mean, it's oscillating back and forth, but because these two are in series, at any instant, the current in one has to equal the current at the other. That's just like conservation of charge. So thinking about things just for the resistor, we know, we have Ohm's law, V equals IR, and we know what this complex value of I is, right? So we have 2.66 milliamps at an angle of 58 degrees, and we're going to multiply that by our resistance, which is 1K at an angle of 0 degrees. So we're multiplying together complex numbers. That means we add these angles together, and 2.66 milliamps times 1K is just 2.66 volts at an angle of 58 degrees. I wrote plus 58 degrees. So this is the complex valued resistance voltage, or the resistor voltage. For our capacitor, we have this same relationship, although it's, I guess really I should have said V equals IZ, and that's why this has an angle of 0 degrees, because it's like in this complex number framework, but we're saying it's on the real axis. For a capacitor, that's not true anymore, right? So we have I still equal to 2.66 at an angle of plus 58, but now ZC is equal to 1592 at an angle of minus 90 degrees. So what happens here is multiplying these two together, we get 4.23 volts at an angle of this plus this is minus 32 degrees. So when we graph these together on the complex plane again, I will erase these. When we graph these on the complex plane, we get something that looks like this. We have 2.5 volts at plus 60 degrees. So that's like, maybe like this. And we have 4.23 volts at negative 32 degrees. So that's going to be something like that, a little longer and a little smaller angle. These are looking kind of similar. So this is VR, this is VC, and these are complex values. Okay, so we do know that the sum of these two complex numbers is just the sum of their vectors on the plane, right? So if we add VR to VC, you can see kind of from the diagram, if I drew it a little better, that we get a vector that is just along the real axis, and that is exactly our 5 volts, 0 degrees, that is our source, and that's because this voltage plus this voltage have to add up to this voltage because that is Kirchhoff's loop law, the voltage law, right? The voltage of the voltage source equals the voltage of the capacitor plus the voltage of the resistor. And that's exactly what we see when we look at it in terms of these complex numbers. So we can think of this whole picture, if we're thinking about things rotating around the complex plane at this rate omega t, we can think of VR and VC, still always being at right angles to each other, but rotating around at this rate, at this same rate, omega t, and having their components oscillate, but still always adding up to this vector, which is also rotating around. Okay, so we'll talk more about these diagrams later, but hopefully this gives you a flavor of why complex impedance is so useful.